All right, we're going to talk about forces. Look how cute this is. Yeah, we're going to talk about forces just a little bit. We're gonna hit forces a smidge now, and then we're going to get back to forces again a little later on in the semester. But Mr. Mitchell and I decided that you can't really talk about the motion of objects if you don't talk about why they're moving. And so in order to do that, we need to talk about forces. What is a force? Fact. Force is push or pull. That's fact. Facts on force. Another fact. The unit is something called the Newton. Not the Fig Newton. No.
We know that Newton was a really smart cookie. Oh, is that where Fig Newtons come from?
No, Fig Newtons are named after a small town in Massachusetts. But don't write that down.
Yeah. Poor Penny. Okay, so unit is the Newton, named after Sir Isaac Newton. It's a push or a pull. We have all these different types of forces. Something called tension, something called friction, applied force. I don't know what that means. That's interesting. Forces can exist where things are touching or when things are not touching. An example of a force where things are not touching would be gravitational. We call these field forces. Okay, so let's just take a little look here. This is my box. There's a cute little cat in the box. And so if we're going to draw forces, then we have to be able to be very clear about what these forces are, which way that they go. So if my box with my cat in it is sitting on the ground, then I have a couple forces acting on it, right? I have a force down, and that force is the force of Earth pulling on the box. That would be what we call the gravitational force. That's a field force. We know this because I can lift my pin up off the tabletop, and if I let it go, it will accelerate down. So there's something here pulling the pin. The pin is not in touch with the Earth, but it's still being acted on by the Earth. So that's a field force. So we have this downward force. This is what we call the gravitational force of the Earth acting on the box. We have an upward force because the box is sitting still. It's not moving down, which means there's got to be a force up, and that upward force is the force of the ground holding the box up. It has a name. It's an odd little name called the normal force, and we'll get to that later. Then if I decide to push, I can push the box, I can pull the box. It just depends on what I want to do. Then I would have another little arrow going this way if I push it or pull it to the right, or I would have an arrow going this way if I push it or pull it to the left. So there you go. FBDs usually are very simple pictures. FBD stands for free body diagram, just like in my last little slide here. Okay. And so if I have a box, I will just draw the box. We usually don't draw a box. We usually just draw a dot, but we'll get into that later. So here's our box. Here's the ground. I have my gravitational force. A lot of people call it F-grav, FG. I usually call it FG, going down. F normal goes up. The force that I am exerting, if I'm pulling the box to the right or if I'm pushing, we call the applied force, usually, or force me. I could call it force Sharky. It really doesn't matter. And the interesting thing is whether I'm pushing or pulling the box, which way is the box going? It's going to the right. So we're going to draw this as an arrow moving from the center of the box to the right. This force over here is our frictional force, which always acts in the opposite direction of the intended motion. And so a free body diagram looks something like this. It's usually very simple, and you usually just draw little arrows, and then you have to put some type of label on them to say what they are, and we will practice this. Anyway, this is what an FBD looks like. It looks something like this. The facts about something called net force. Net force, what is this? Net means total, right? Like your net take-home pay is your total take-home pay. So the net force is the total force acting on something. It's if you add up all the forces acting on something, that's your net force or your total force. Net force is still measured in newtons. A net force can move something. No, it doesn't have to. Net forces can be, well, let's take a look at this box right here. What is the net force acting on that box? Well, if I have two people pulling in opposite directions, and both of the forces are the same, is this box going to move? And the answer is no, it isn't going to move. Okay. Our net force in this case is going to be 0. Why is this? Well, a force to the right and a force to the left are different. If I ask people, are these forces the same? I have a lot of people tell me, yes, those forces are the same. They're not. This force to the right is very different from that force to the left. The numbers are the same. So what we say in physics language is we say the magnitudes of the forces are the same. But their directions are different, which means they're not the same force. So if they're going in opposite directions, what we do is we subtract. Now sometimes, just like in this picture here, the two forces are not the same size. So what happens? If your two forces are not the same size, well, then you're going to have some acceleration. You're going to have something move, and it's going to move which way? To the right. That's the thing. So here's some practice problems. See if you guys can pull this off. I have two people pushing in the same direction. So we add those two forces. We get a net force of 70 newtons. Notice the little arrows. The bigger the number, the bigger the force, the bigger the arrow. The number is the magnitude. So we say the magnitude of this force is 40 newtons. The direction is to the right. So they're both going the same way. We can add them up. Our net force would be 70. Here, our two forces are going in opposite directions. So we subtract. In either case, we are going to have an acceleration on the box. This box is going to go to the right. It has a force of 70 newtons. Probably going to pick up speed. This box is also going to go to the right. See that little green arrow? The total force is 10 newtons. And it's going to pick up speed also, just not quite as much. And then we have something crazy like this. And that looks scary. And we're going to talk about this. We're going to talk about right triangles in just a little bit in this first week. So here you have two forces that are acting at right angles and something different happens. We'll get there. Okay. Here's F-net practice. Can you get the net force acting on this box? What is it? This is box 1. Go. Here's box 2. Can you get the net force acting on this box? This is box 2. Do it. Go. Box 3. Net force. What is it? Box 4. Net force. Go. How do we measure forces? We measure forces using a spring scale. We got a little spring scale here. It's called a spring scale because, I'm going to make myself bigger. It has a spring in it. See that little spring there? The spring will stretch. We're talking about springs later in the year. The stretch of the spring will tell us exactly how much force we have. So this is a thing. Okay. Hopefully we'll get in the classroom and get to use these things. So if you put something here, the spring will stretch. And that's what happens. A few other things. There's this term called inertia. Inertia is misunderstood. A lot of people will use this term, and they use it incorrectly. Inertia has to do with the reluctance of something to change. So if you talk about inertia of something, something that's very big is going to have a lot of inertia because it's hard to get it to move, or it's hard to stop it if it's already moving. I always use the example of trains in class. A train is something that's very big, that's hard to get to move, and then once they get going, it's hard to stop them. So you got this little graphic right here. It's so cute, right? The elephant has more inertia than the person because it has more mass. It's more reluctant to change. It's hard to get those dang things to move. I know. I used to work at the zoo. They're hard to move unless they want to. And they like classic rock. But that's neither here nor there. Okay. Because something with more mass has more inertia, what I usually tell my students is that inertia and mass are synonymous. In other words, those two terms essentially are the same. So if you have more inertia, you have more mass. Okay. What the heck is mass? Well, mass is the amount of matter inside of something, what it's made out of. Mass is an intrinsic property. Mass doesn't change unless you add more, right? So if you sit on your butt a lot and eat pizza, like some of us have been doing during the shutdown, then you're going to have more mass. Okay. Now, if I were to shoot you up to the moon right now, you would still look like you. So your mass doesn't change. If I shoot you out into space, you're still going to look like you. Your mass doesn't change by virtue of position. Okay. It's an amount of matter in something. The unit for mass is the kilogram, or kg. There we go. So, I can't see. Make sure you understand that distinction there. Couple of other little things. Equilibrium is the term we use when all the forces are balanced. Everything is balanced on something, which means our net force is zero. Equilibrium can be hard to understand. Most of the time people will tell me that something is not moving, which is true. So if something's not moving, then all the forces are balanced. I'm sitting in my chair right now, so I have balanced forces acting on me. But can you have balanced forces while you're moving? And the answer is yes. If a plane is flying, and that plane has a thrust this way, and it's running into air that way, if those two forces are balanced, then the plane will fall from the sky? No, it will move at constant speed. Okay? I always use the example of someone jumping out of a very tall building, right? If they jump and they go faster and faster and faster and faster, at some point, the gravitational force down will be equal to the air pushing up. And what happens? They're saved. They stop, right? No. They move at a constant speed, which I like to call cruise control. And that's the thing. But yes, equilibrium is something that happens. It's when your net force is equal to zero. That's a fact. Here are some examples of net forces being zero. Okay? So, just know that this is a thing. What if something is not at equilibrium? Well, then you have unbalanced forces, and we talked about this already. Something is going to move, and when we say something moves, what we really mean is something accelerates. Accelerates. That word we're gonna hit before too long. All right. Hope this makes sense. Thanks, guys.